Everyone, this is Hongliang Tian and Chuan Song. We'll talk about Asterinas, a new Rust-based OS kernel that we have built from scratch for TE and probably some more use cases. The talk is divided into three parts. First, I will provide some background knowledge about IAGO attacks. In particular, I will show how IAGO attacks affect Linux kernel's memory safety. Then I will present Asterinas, a new Rust OS kernel that provides high assurance of memory safety despite of IAGO attacks. Last, my partner Edmund will elaborate on how Asterinas is ported to Intel TDX. I'm hoping that by the end of this talk, you'll be convinced that the Asterinas is an attractive option as a TOS. Without further ado, let's begin with the first part. As we all know, Linux is prone to memory safety bugs. But do IAGO attacks make the matter even worse? Or to what extent? Let me show you by examples. In the first code snippet, the variable named this is an array of descriptors that are shared by both the T and the host. So the highlighted value of this index I.next is untrusted. What is the consequence of assigning this untrusted value to the variable I on the left? Obviously, you got an out-of-bound index bug. In the second example, this port's device struct is controlled by the untrusted device. As a result, the values of number ports and number queues are controlled by the device. Then what is the security risk here? It turns out that the number queues variable may end up with a value of 0 because of arithmetic overflow. The kmalloc array function then alloc a 0-size object successfully, but using this object will cause you illegal memory access. The third example is about virtual net driver. The highlighted variable MTU is controlled by the device. So the malicious device may provide an abnormally small value. This leads to the execution of a very rare branch. The driver also attempts to handle the rare situation by going to the free label and exiting the function. But the problem is that this error handling itself is buggy. You see, before jumping to the free label, it should have set a proper error number to the error variable, but it didn't. So the prop function returns a success, even though it has actually failed and has freed the device object. So the end result is a use after free bug. These three examples should have given you a sense of how IAGO attacks threaten the memory safety of Linux as a TOS. According to Intel's estimation, there are over 1,500 locations of untrusted inputs in Linux. And if you take into account that around 60% to 70% security vulnerabilities are rooted in memory safety bugs, you should agree that the situation isn't looking good, right? Now that we are on the same page regarding the security threat posed by IAGO attack to a TOS, let's move forward to part 2 and explore how Asterinas can do a better job than Linux. Asterinas is a secure, fast, and general-purpose OS kernel written in Rust and compatible with Linux. It targets use cases where you want to run Linux and you want to run and modify Linux applications. So you want Linux ABI, but Linux itself is considered insecure given its sheer size of TCP and its nature of being memory unsafe. One such example is TE. Asterinas is not yet another Rust OS. It's different. Let me first provide some background knowledge. The knowledge is that, unlike many of you may believe, a Rust kernel is not necessarily a memory-safe kernel. The reason is that there is this thing called the unsafe keyword. It is the source of all the superpowers in Rust. It allows one to do many really risky stuff, like dereferencing row pointers or mixing assembly code with Rust code. When you are a Rust application developer, you rarely need to use the unsafe superpowers. But if you are a Rust kernel developer, You can't do your job without it, because all the low-level operations demand unsafe, like manipulating CPU registers or accessing physical memories. So you end up having a Rust kernel with safe and unsafe Rust code mixed up. And you can't be sure that all the unsafe code spread across the entire code base aren't going to cause you any problem. To address this shortcoming of existing Rust kernels, we propose the framekernel OS architecture. In this OS architecture, the entire OS resides in the same address space like a monolithic kernel, and is required to be written in Rust. However, there's a twist. The kernel is partitioned in two halves, the OS framework, akin to a microkernel, and the OS services. Only the OS framework is allowed to use unsafe Rust, while the OS services must be written exclusively in safe Rust. The OS framework is responsible for encapsulating low-level unsafe code into high-level safe abstractions, while the OS services implement most of the OS functionalities, including device drivers. To understand the advantage of a frame kernel, let's compare it with a monolithic kernel and a microkernel. Now that we have restricted the scope of unsafe Rust, the memory safety of a frame kernel can be reduced to that of the OS framework. This gave us a minimized TCB, like a microkernel. On the other hand, the single address space allows different parts of a frame kernel to communicate with the most efficient means, like function calls and shared memory. So the efficiency of a frame kernel is on par with that of a monolithic kernel. While this idea of a frame kernel sounds quite simple, it's challenging to build one. Specifically, the OS framework has to meet these four conflicting requirements: expressiveness, soundness, minimalism, and efficiency. Among these four requirements, the concept of soundness deserves the most explanations. The Rust programming language sets a high bar for soundness. For a specific use case, these are our OS framework, it has to guarantee that the kernel won't have any undefined behavior. So regardless of how one may write the safe OS services, regardless of how the CPU may execute the kernel concurrently, and regardless of how the environment may provide inputs to the kernel. This definition of soundness implies that the frame kernel is naturally resistant to the untrusted inputs from IAGO attack. We have designed and implemented Asterinas framework, and as an OS framework for building frame kernels, it satisfies all the aforementioned requirements. To guarantee soundness, Asterinas framework is designed to follow one key principle, which is to distinguish between typed and untyped memory. Typed memory is the one that may affect Rust memory safety or type safety. In particular, the memory pages that contain Rust code or data are considered typed. Untyped memory, on the other hand, cannot affect Rust memory safety or type safety. It consists of all the memory pages that are valid to use by the kernel but are not marked as typed yet. The framework API only allows access to the untyped memory through some safe abstractions. These abstractions represent different kinds of untyped memory, like a physical memory page or the address space of user program. These abstractions provide some carefully designed safe methods, which can be used as an alternative to the old and unsafe means of row pointer dereferencing. Asterinas is a kernel built upon Asterinas framework. Let's see how Asterinas' approach to defending IAGO attack is different from Linux approach. Linux attempts to harden this huge attack surface by auditing, fuzzing, testing, and fixing every allowed driver. In contrast, Asterinas do not have much to worry about. This is because all the drivers for peripheral devices are written in safe Rust. Their only chance of affecting memory safety is through the safe APIs provided by the framework. But they have been carefully designed and implemented to prevent any invalid memory access. For this reason, we argue that Asterinas is more memory safe than Linux or any other Rust kernels, especially in face of IACO attacks. Asterinas has been open sourced. We have implemented enough number of system calls and drivers to run some really interesting and unmodified Linux applications. The project is not ready for production usage yet, but we'll get there this year. At least that is the plan. And since Asterinas is a perfect fit as TOS, we're really optimistic about getting early adoptions from the field of confidential computing. And this brings us to part 3. My partner Edmund Song from Intel will share his experience of porting Asterinas to Intel TDX.
Okay, thank you, Hongliang, for introduction. Hello, everyone. I'm Edmund Song, Intel Principal Engineer. For next 10 minutes, I'm going to discuss how to get Intel TDX enabled for running Asterinas as TD guest kernel. Intel TDX technology enabled a hardware-based trust execution environment for cloud workloads. TDX is based on virtualization technology with extensions for confidential computing requirements. The trust execution environment built upon TDX is also named as trust domain, or TD. We can use TD to host a full virtualization instance. Applications, whether based on VM or virtualization container, can directly run in trust domain. And users can use lift and shift model to migrate cloud applications from legacy computing to confidential computing without any need to modify code. TDX integrates a multi-key memory encryption engine into processor's memory controller. This engine can enable in-flight data confidentiality for complicated cloud environment. In addition, the TDX instruction module isolates hypervisor from access to sensitive instance information. So by removing hypervisor and operation system from trust boundary of TD instance, we can simplify the effort for building a trust environment in cloud. TDX TCB. TCB, also known as Trust Computing Base, is the foundation for building trust and building security. The TCB of TDX is limited to silicon-wide, including processor core, register, cache, memory controller, and the most fundamental firmwares. See TDX instruction module. This way can reduce the attack surface and minimize the cost of building trust in cloud environment. To meet confidential computing requirements, TDX introduced a bunch of microarchitecture level enforcements to harden data protection for VM. In virtualization environment, the guest kernel or guest runtime for running user application consists of many different modules, like process and thread management, scheduler, memory management, and a driver framework with different device driver support. We can always divide these components into TDX agnostic portion and TDX enlightened portion. So most of TDX modifications for guest kernel fall into the bootup module, exception module, memory and MMIO management module. TDX guest create. To easier TDX guest enablement, we developed one open source project to encapsulate TDX instruction access and TD guest flow into single Rust crate. This crate can be integrated with different guest kernel or guest runtime to get the kernel runtime running as TDX guest. TDX guest crate supports two kinds of interface. The first one is TDX guest ABI, CNTD call, TDVM call, defined in TDX ABI spec. The second interface is to wrap typical TDX guest flow into some functions, like TD initialization flow, virtualization exception flow, memory management, and attestation flow. I will discuss more details in following 2 pages on virtualization exception and memory management flow. Okay, let us look at virtualization exception. Virtualization exception is one TDX specific type to handle some instruction access or register access. Such accesses are not allowed in TDGuest environment. As we have talked, confidential computing brings some microarchitecture level enforcement to virtualization for security considerations. Such enforcements are beyond legacy virtualization support. It means that some code or some resource access valid in legacy instance are not allowed to directly run in TDGuest environment. So when such cases happened, the CPU microarchitecture will trigger special CPU cycles to inject one exception into TDGuest. This exception is virtualization exception, also known as VE. To handle VE, we need to set up one VE handler in TD enlightened guest. And in this handler, we need code to analyze exception context and virtualize the request operation for non-enlightened portions. Memory management. In order to prevent user-sensitive data from illegal access, TDX architecture separates guest memory into private GPA and shared GPA. The private GPA can only be accessed by TD itself. The shared GPA can be used by TD guest to exchange data with outside of the world, like a hypervisor or device. The page table set up for private memory is defined as secure EPT. We must go through TDX instruction module for the access of secure EPT. To secure private memory management, TDX guests need additional memory management flow. The first one is allocation. When VMM needs to allocate a page to guest, the page allocated to the guest is set as pending state. And only if TD guest accepted this page as private memory can it be accessed by TD software as normal memory. There is also one case for converting the page between private memory and shared memory. So here is the flow. As a first step, TD guest needs to notify VMM for page remapping. VMM will call TDX instruction module to remap the page to either shared EPT or secure EPT. If the remapping is from shared page to private page, so the TD guest need additional page acceptance flow. We have been working with Hongliang's team to successfully run Asterinas as TD guest based on Intel Xeon platform. Here are some features we have supported. The basic flow for running Asterinas as TDX, like initialization, exception management, memory, and MMIO access. We also enabled some commonly used devices and drivers for TD environment, like virtual I/O, console drivers, block device driver, network driver, and attestation support. For future, we will work with Asterinas for getting more TDX feature enabled. Also, we have planned to streamline the debug function and the trust management function at the service layer for Asterinas. We plan to do more tests with real cloud workloads with Asterinas. We also need to do some tests for more devices and performance benchmark. So that's all for our today's sharing. Thank you all for attending our presentation.